So, let's talk about AI. What if I told you that the very computers powering this revolution are built on a fundamentally flawed foundation? Well, today we are digging into a new research paper that proposes a radical new way to build AI hardware, one that promises a mind-blowing leap in energy efficiency. It could honestly change everything.
And believe me, that change needs to happen like yesterday, because right now, AI is on a collision course with our power grid. Get this, a recent projection suggests that by 2030, AI data centers alone could be eating up a staggering 10% of all the energy we produce here in the US. That's just not sustainable. Something's got to give.
So, how do we get out of this mess? Well, as this quote from the paper points out, researchers are hunting for a whole new kind of computer. Now, they use fancy words like stochastic or probabilistic, but all that really means is a computer that's designed from the ground up to work with randomness and uncertainty, which, is the exact kind of math that makes modern AI tick. This could be our ticket out of this energy crisis.
We're pouring billions, maybe trillions of dollars into AI, but the energy bill is just shocking. And it begs a really basic question. Are we even using the right tools for this? And according to this paper, the answer is a big no. Our whole approach is super inefficient. But here's the wild part. It wasn't on purpose. It was basically a historical accident, something they call the hardware lottery.
So what on earth is the hardware lottery? Well, think about it. The AI models we use today, like the big language models, they weren't chosen because they were the smartest or the most efficient. Nope, they were chosen because they just happened to work really well on the hardware we had lying around. GPUs. And GPUs, they were made for video games. It's kind of like jamming a Formula One engine into a submarine. Yeah, it might move, but it's going to be clumsy and burn a ridiculous amount of fuel.
Okay, so if GPUs are the wrong engine, what's the right one? Well, that brings us to this really cool idea called energy-based models, or EBMs. Instead of just guessing the next word in a sentence, these models try to figure out the underlying structure of reality. They assign a score, they call it energy, to everything. So a normal picture of a dog, low energy, totally plausible. A picture of a dog with, wings, super high energy, because that's just not a thing.
And this is where it gets really visual. Check this out. The EBM creates this energy landscape, kind of like a mountain range. All the possible dog pictures are down in one deep valley. All the airplane pictures are in another. Now, to make a new image, the model is like a hiker dropped into this landscape. And here's the problem. If it lands in the dog valley, it gets stuck. And climbing over that huge mountain to get to the airplane valley, it takes a ton of time and energy.
And that right there, that's the fundamental problem. Researchers have a name for it. The mixing-expressivity tradeoff. It's a mouthful, but the idea is simple. The smarter and more powerful you make your AI, the crazier its mountain range gets, more peaks, deeper valleys, which means it gets stuck more easily, and the energy bill just goes through the roof.
So for a long time, this trade-off seemed like a law of nature. You want a smart model, you pay the energy price, period. But, and this is the really cool part, the folks behind this paper found a way to completely bypass it. They don't try to climb the whole mountain range at once. They found a much, much smarter way.
So here's the billion-dollar question, right? How can you get a model that's really complex and powerful, but without it getting stuck all the time? How do you get all that creative power without the insane energy penalty?
And the answer is a brilliant little thing called a Denoising Thermodynamic Model, or a DTM. And the genius of it is this. Instead of building one massive, complicated model, a DTM links a bunch of really simple ones together in a chain. Each little model in the chain has a super simple job to do.
The best way to think about it is like a sculptor. The old way, that's like wandering a mountain range hoping to stumble upon a finished statue. It's nuts. The new DTM way is like starting with a block of random noise, just static, and then you make one small, easy tap with a chisel, then another, and another. Each tap is a simple, low-energy step that slowly, gradually, turns that random noise into something amazing. And you don't have to take my word for it. Look at this. This is it in action. That top row, that's just TV static, pure noise. Then, as you go down row by row, each one is another one of those chisel taps. And you can literally see these images of clothes and shoes emerging from the chaos. It's just so elegant, isn't it?
Okay, so this is all great in theory. But here's what makes this paper so important. It's not just theory. They've actually designed a computer to do this, a blueprint for a real chip using tech we already have today.
So let's talk about the hardware. The key phrase here is all-transistor design. Now that might sound boring, but it's huge. Why? Because other people have tried to build computers like this before, but they used all sorts of weird, exotic materials that you just can't manufacture at scale. This new design? It uses the same basic building blocks, transistors, that are in the chip in your phone. That means we can build it in the factories we already have. It's actually practical.
And at the very heart of this new chip is one key breakthrough. It's a tiny, super fast, and incredibly efficient random number generator. Remember how the whole process starts with random noise? Well, this little guy is what makes that noise. It's the engine that powers the whole denoising process, and it's built from the same stuff we've been using for decades.
All right, so we've got a new way of thinking about the problem, the DTM model, and we've got a new computer chip designed to run it. So what happens when you put them together? Just how much better is it? Well, the results are, to put it mildly, absolutely staggering.
We're not talking about a small improvement here. We're talking about a radical leap forward, a complete game changer for AI efficiency.
Okay, just look at this chart. On the left, that big bar, that's the energy a normal GPU uses for one task. The one in the middle is an older attempt at a probabilistic computer. Still pretty high. And then, look all the way over on the right. See that tiny little sliver? That's the new DTM computer. You can barely even see it. The difference is just insane.
So let's just put a number on that. To do the exact same job, creating the exact same quality image, this new system uses, get this, 10,000 times less energy than a top-of-the-line GPU. I'm going to say that again because it's hard to wrap your head around. Not 10%, not 10 times, 10,000 times more efficient. So what does this actually mean for the future of AI? Well, the researchers are pretty clear. This new computer isn't going to replace GPUs overnight. That's not the point. Instead, they see a future of hybrid AI systems. You'd have our traditional computers, like GPUs, working right alongside these new, super efficient, probabilistic ones. You know, using the right tool for the right job.
And that leaves us with a really fascinating thought to end on. Maybe the future of AI isn't about building one giant, all-powerful brain that just keeps getting bigger and bigger. Maybe the real future is a whole team of specialized minds. A diverse collection of different kinds of computer chips all working together, each playing to its strengths. A future that's not just more powerful, but a whole lot smarter and way more sustainable.